Nanomaterials hold promise for groundbreaking applications ranging from medicine to energy, and we're going to hear a few examples of those. And together with physics-based modeling and human understanding, these AI algorithms really have great promise to analyze the vast data sets, identify patterns, and accelerate the prediction of these novel nanomaterials for applications. So with that, I'd like to introduce our first speaker, Professor, and now I'll get your name wrong, please correct me, Qian? Chen is a professor and the Radcliffe Scholar in the MATC department at Urbana-Champaign. She obtained her PhD degree there years ago, left for a postdoc, and then came back. And she's been doing outstanding work since that time. She has an array of awards, including the Forbes 30 Under 30 Science List, a range of Young Investigator medals from the AFOSR, YIP to the Career Award. And she was recently named the MRS Outstanding Early Career Investigator Award in 2024. So this is really, really quite amazing, and we'd love to hear her presentation on electron videography and its automation for nanoparticles.
Thank Kate for the introduction and invitation. Hi everyone, this is Qian. It's my greatest pleasure to share with you our thoughts on AI and our efforts on electron videography and its automation for colloidal nanoparticles. So let me start my talk by going all the way back to 20 years ago. 20 years ago, I was an undergrad student. I was doing wet chemistry synthesis experiment, which was labor intensive. The products I synthesized were nanomaterials. So I need to use this transmission electron microscopy, or TEM, to characterize the size, shape, and spatial distribution of the sample at atomic to nanometer resolution. So those are TEM images published in my first research paper. But some of you might not really know, at that time, those images were not taken by digital cameras. Instead, those are actually taken by films. You need to develop the film and then translate the film into a digital micrograph. Time has flown. So now if you ask the AI agent, how does the material synthesis lab look like? This is a photo generated by ChatGPT. And I promise this is the only AI-generated schematic in my entire talk. So if you look at this image, you can see it captures some interesting features. In particular, it's highlighting the robotic synthesis that is high throughput. So why does our ChatGPT capture this feature? And that's because that's something that we have witnessed a lot of advancement in the field. So 4 years ago, there's this beautiful paper showing how a robot can move around to do chemical synthesis. They can actually do the liquid handling. They can actually weigh the chemicals, initiate the reaction. They can even collect the products for gas chromatography characterization to know what is the identity of the chemicals. And this is about automated synthesis of small molecules. And then as we move into nanomaterials, things can be more complicated. And for my talk today, I'm going to focus on colloidal nanoparticles. But the lesson that we learn from colloidal nanoparticles can also be extrapolated to other nanomaterials. So why do we care about colloidal nanoparticles? This is a photo of my former PhD student, Yang, who is now a Schmidt Science Fellow at Caltech. In her hands, she was holding some colloidal nanoparticle suspension. So those are great nanomaterials because you can synthesize them in large quantity. They can be solution processable. They have very rich properties. For example, they are the red color in the rapid COVID test. And the semiconductor nanoparticles, as introduced earlier, the quantum dots, actually win the Nobel Prize last year. So as people try to transfer the automated synthesis from molecules to nanoparticles, of course, we can do liquid handling beautifully, as shown in this animation from Nano's group at University of Washington. And then on the right is a schematic that is drawn by my colleague, Paul Kenneth, showing how you can connect such automated synthesis with characterization. But I want to mention, in both the molecule synthesis and also this quantum dot or nanoparticle synthesis workflow, The characterization people have been using is largely ensemble spectroscopy characterization, such as UV-Vis, fluorescence, XRD. So those ensemble characterizations are wonderful because they can be easily made into high throughput. So that's why it's easy to integrate them into a synthesis loop. The data generated from those analysis methods is also relatively easy to interpret. However, this is not really enough because when it comes to nanoparticles, they are way more complicated than molecules. So shown here, a nanoparticle has its size, shape, atomic arrangement, interface, defects, composition, and all those features as shown in this beautiful series of papers here are closely related to their property and their performance and their function. And those properties can only be captured using electron microscopy. So that's why TEM has been an indispensable component in nanoparticle research. We need to utilize this real space imaging capability at this otherwise inaccessible nanometer to atomic resolution. But the reason why TEM has not been included in those automated materials discovery platform is because it has limitations. So TEM is notoriously low throughput. In this photo, my former PhD student, Phonon, she basically had to sit in the dark room of electron microscope for hours to manually select region of interest, to manually do the alignment of the microscope to collect images. Also, data analysis on those complicated images shown here can be also complicated. So that's why it has been hard to achieve even just automated data collection using electron microscope, let alone to integrate them into the complete synthesis loop. So that situation motivates my talk today. So in my talk today, I'm going to show you what is the latest TEM development to give you a little bit of motivation because it's really enabling innovations in nanomaterials research. I'm going to talk about what is the interaction between TEM and data science methods. And I'd like to also highlight two quotes from my postdocs. So one quote is from my postdoc, Chen, who is an expert in nanoparticle synthesis. Her quote is, "High throughput synthesis alone can be wasteful." So we need to use a scientific intuition and also high resolution characterization to make sure we don't need to really just overwhelmingly sample the huge synthetic parameter space. The other quote is from my other postdoc, Qian. His quote is that AI-guided nanomaterial research right now is not necessarily limited by the throughput of the synthesis. It's actually more limited by the throughput of TEM characterization. Since I have been talking about TEM, of course, my lab has been focusing on TEM. So in particular, my lab has been developing and utilizing this suite of tools which we refer to as electron videography. So electron videography goes beyond just taking one single snapshot of a sample. Instead, we can take movies. And in my group, we have 3 different ways to take movies. So the first is liquid phase TEM, as shown in this animation, where you can actually sandwich and seal a colloidal particle suspension in the liquid phase TEM chamber. So by doing so, not only you can resolve the nanostructure, you can also see the vivid dynamics in the presence of solution. The second is electron tomography, where you can actually resolve the complicated 3-dimensional structure of a sample at the otherwise inaccessible sub-nanometer voxel resolution. And the last one is 4D scan, which allow you to image the defects, strain, crystalline phase, and crystal phase orientation at the nanometer resolution. So all those 3 electron videography methods are fairly recent. So that's why we're able to utilize those methods to study a diversity of systems. For example, we can take movies of colloidal nanoparticles on their phase transition. We can take movies now of proteins dynamically transformed in solution in real space and real time. We can take movies of polymer morphing. We can also take movies of electrochemical reactions, which is very important for energy storage and conversion. So out of all those first-hand experiments with those different systems, we realized repeatedly the order and heterogeneity at the nano to atomic level can really impact their bulk performance. So that's why real space characterization methods are very important. So for today's talk, I'm going to focus on the first type of movies. In particular, we're going to look into how the formation and relaxation of nanoparticle self-assemblies happen. So why do we care about nanoparticle self-assemblies? I already mentioned individual nanoparticles that have interesting property, but when they're put together through self-assembly, they start to have crosstalk, and that crosstalk can lead to collective properties that is sensitively dependent on the structure. However, for a long time, what people know about that structure is literally the single snapshots of the final structure. We do not really know the self-assembly pathway, and we cannot really engineer them efficiently. In the meantime, modeling this process has been difficult because the colloidal interaction at the nanoscale has been non-additive. So here comes my group's unique contribution. So we introduced liquid phase TEM to observe the self-assembly pathways of nanoparticles. In particular, we use this type of microfabricated chamber, which allows you to do in situ TEM imaging together with modulation of the liquid environment. But before we go too far, let's actually keep in mind, electron beam has a high energy, so you can easily initiate beam-induced nanoparticle reaction as shown here. You can just see the nanoparticle are getting etched away in the liquid. And that's what we want to avoid. So that's why when I started my career 9 years ago, the first few papers coming out of my group are essentially control experiments funded by my NSF Career Award by the Solid State and Materials Chemistry program, where we're able to identify an imaging dose condition within which we do not need to worry about nanoparticle reactions induced by electron beam. So with that being established, in 2020, we published our first paper on liquid phase TEM imaging of nanoparticle self-assembly. So this work was done by my former PhD student, Hao, who is now a faculty. So this is a liquid phase TEM movie. The dark shapes are nanoparticles that are in solution. So they are dynamic because they are undergoing Brownian motion. At the same time, they can interact with each other to form into a crystal. We're able to do single particle tracking to follow the position of particles to allow us to chart the crystallization coordinate as shown here. So this actually tells us, in the end, this system goes through this non-classical nucleation pathway. And this is a pathway that has been identified in atomic molecular protein system before. We identified it for the first time for nanoparticle superlattice. I'd like to mention we tried a lot of efforts to make sure such taking of experimental movie is quantitatively reproducible, which is summarized in our 75-page support information. I'd like to mention our effort to be able to go beyond just taking beautiful movies but get statistical mechanics-based understanding is because I'm able to process the liquid phase TEM movies automatically. So my student, Le Han, was able to develop this neural network method where the input can be our experimental liquid phase TEM images, and the output can be the size, shape, orientation of the particles. So previously, when you think about such image analysis, you need training data set. And then people usually do the manually annotated image as training data set, which is labor intensive, which is subject to human bias. So the real innovation of this work, going beyond just as the first demonstration how to use machine learning for liquid phase TEM data analysis, is that Le Han developed this complete workflow to show how you can simulate liquid phase TEM images with all the noise patterns, just like what we will get from experiments. And this can build a really robust training data set with very well-controlled ground truth. So that's actually why this method is really trustable. And now we have this method, we dive into an even difficult question to study for nanoparticle self-assembly, which is what is happening after nucleation. So this is called growth habit, which is a concept we also learn from atomic crystallization. So as shown here, even if you start from the same nuclei with different growth environment, you will have crystals of different size, shape, and surface morphology. So we want to study the same phenomenon with nanoparticle building blocks. And my student Bingbing was able to subsequently upgrade our liquid phase TEM procedure. So now we can actually watch the growth of a large crystal in 3 dimensions. So in this liquid phase TEM movie, you can see the incoming particles will form into one layer before they grow another layer. So this is a so-called layer by layer growth to ensure a flat surface. And then if you look at the other two particle shapes, although the interaction, the lattice symmetry is very different, they also follow the same layer by layer growth. But does it mean nanoparticles will always follow this one single growth mode? And that's not really the case. So in our experiment, we're able to actually resolve two different growth directions, the in-plane growth and out-of-plane growth. And we found that we can actually have hybrid growth modes. So in these two liquid phase TM movies here, the particles of the same color means they're in the same plane. So for the top movie, you're looking at a corrugated out-of-plane growth by very smooth in-plane growth. And then to the movie below, you're looking at layer by layer out-of-plane growth and very corrugated in-plane growth. This is also the first time people are able to experimentally image such hybrid growth modes. So to really understand what is driving these different growth modes, my collaborator, Professor Eric Lawton of Northwestern, was able to come up with this kinetic multicolor simulation, which can reproduce all the four experimentally observed growth modes. And in addition, he was able to provide this phase diagram. So if you look at this phase diagram, building blocks of different sizes, they occupy different regions. Interesting for nanoparticles, you can occupy all the four growth regions. And that's why with nanoparticles, a building block, you can have a rich diversity in crystal engineering. So this type of work is more or less fundamental. And at one point, we started to have a new ambition. That is, how can we change our role from the passive photographer of the movie to the director of the movie? How can we actually engineer the pathway and actually make new materials? So what do I mean by new materials? This all goes back to when I had a very nice conversation with my longtime friend, Professor Xiaoming Mao in University of Michigan. So in her field, you will really look at mechanical metamaterials where you utilize the geometry to encode interesting mechanical properties. And then fundamentally, this is because you can see structures as beads connected by springs. So when you agitate the structure, you will induce Phonon vibrations, and that will really correspond to the mechanical response. Quantitatively, this is measured by this Phonon dispersion relationship, where the x-axis is the position of the first Fourier zone, the y-axis is the Phonon frequency. So from this Phonon dispersion relationship, you can basically read all the mechanical property features showing out there. But for a long time in her field, people only care about atomic lattices, care about microscopy, fundamentally microfabricated structures. So we put our ideas together to think about how about self-assembled mechanical nanomaterials made out of nanoparticles. That could be interesting because that has been barely charted. That can actually enter into a completely different length, frequency, force scale, and fundamentally that could also pose the question how to measure phonon behaviors at this length scale. Since geometry is the key, I'm going to focus on one geometry of Maxwell lattice that is very popular in condensed matter physics. And my student Chris was able to actually assemble the first nanoscale Maxwell lattice shown in this liquid phase TM movie. So if you look closely into this movie, different from all the movies I showed you earlier, now you can have collective lattice vibration or reorganization. And that's because this is a Maxwell lattice. It can freely distort without paying any energy penalty. So how do we measure the phonon response? So as I mentioned earlier, using machine learning, we're able to accurately measure the particle position with sub-nanometer precision. So we can measure what is the displacement of the particles at the local lattice site. And this displacement field actually allows us to ultimately derive the phonon dispersion relationship shown here. So this is the same phonon dispersion relations as I showed you earlier, but this is the first time we're able to measure it using nanoparticle superlattice. I'd like to highlight, for example, you can see a low energy band showing here, which is corresponding to soft modes of a Maxwell lattice. We're also able to develop a B-spring model for our complicated nanoparticle system, which matches really well with our measurement, which can allow us to measure what is the spring constant for the first time at the nanoscale. This method does not require any information about the particle size, shape, and interaction. We can do aerial propagation to make our measurement as really accurate. And then based on this measurement, we start to ask how to actually engineer the phonon dispersions. So because we have quantitative measurement, we're quickly arriving at the conclusion that first, we can actually change the interparticle interaction, which can actually increase the phonon frequency. We can also change the lattice symmetry, which can actually change the topology of phonon dispersion. For example, in the hexagonal lattice, we no longer have soft modes because now the lattice is very overly constrained. We can also go to even more complicated soft lattices shown in there with the soft shear modes. So with those two engineering understanding implemented, now we can imagine that basically unlimited opportunity for nanoparticle self-assemble mechanical metamaterials, because we have a huge library of particle shape, a huge library of self-assembly structure. You can always have new different ways to engineer the interparticle interaction. So this is our synthetic effort to make patching nanoparticles, where the collaboration with Sharon Glauser on understanding the formation was supported by the NSF STC Center on complex particles and complex particle systems. So from this series of studies, you can tell how the integration of electron videography with machine learning-based data analysis can help us get better scientific intuition, can actually guide us with better materials design. And I actually mentioned this effort of having automated TEM data analysis for complex nanomaterials is really popular now in my group and also in the TEM community. But this is not really the ending point. So we need to really transition from the low throughput TEM experiment to high throughput automated data collection. So in this last slide, I'm going to go back to the code, how to increase the throughput of TEM. So this is the effort of my postdoc Xinzhi, where he's able to basically ask the TEM, the electron microscope, to automatically and smartly search over TEM grid. So now the data can be automatically obtained, and in the same time, he was able to incorporate smart online image analysis to inform the microscope where to go. So we really see this as a way to really make our TEM characterization into a macro scale, just like spectroscopy characterization with high throughput. This can allow us to see what is previously not possible to see, now with much higher throughput. This can also move towards truly incorporating electron microscopy into the synthesis loop of nanomaterials. So with that, I'd like to thank you for your attention. I'd like to end with a remark that the best is yet to come.